Okay, before we continue, let's have a short talk about telecommunication. I'm sure you all have such a nice smartphone in your pockets, so I don't have to explain this to you. You know it much better than I do, mostly. But what's behind the telecommunication network? There is, first of all, there's a base station your mobile phone is talking to, mostly visible by these nice antennas. This is the mini base station, which is maybe located in something like a shopping mall. This is a very small package here. You have those nice antennas. This is a base station your mobile phone is directly talking to, but there's much more in the background. So we have systems which we call MME, which is responsible for the handovers between radio cells. We have an HSS, which is a database, which is having your credentials, which knows what kind of data you are allowed to retrieve, your user credentials and such. PCRF is responsible for the data access. This one is really limiting your bandwidth, giving you a bandwidth of maybe 10 kilobytes per second or whatever your contract is saying. We have two gateways which are forwarding the traffic into the internet. So you have much more systems in the background. So this is the hardware of such a network. Some amount of numbers. So if you look to Germany, and here on the top I put maybe a picture showing you the radio cells in Munich. And if you look to it in detail, you will see a radio cell is something not much more than one or two streets in city areas, in downtown areas. If you look to some numbers, sorry for having those old numbers, but I did get newer ones. German Telecom has about roughly 40 million subscribers in Germany. In total, we have more than 100 million subscribers, so we actually have more mobile network subscribers than we have people in Germany. From those radio cells, we have roughly about 70,000 in Germany, and the total data volume is about 100 million gigabytes per year. And if you look to the number of calls and SMS per day and the number of internet connections per day, these are really huge numbers. And especially today, the smartphone is always on, so this never stops. This is always on 24 hours a day. So this gives you a nice idea about the amount of data, about the amount of knowledge we have. This is another picture also showing Munich. In those bubbles, you will see how many base stations are in this area. These are pretty high numbers. And this is the area of main station in Munich. And you can see that even in a single main station, you have several base station locations. So this is a pretty crowded space. And handling all those networks and all this data you get from those radio cells and other installations from the network is a huge and demanding task. Some words about big data. Also, my title is Big Data Analytics. I'll tell you one of my secrets, which means big data is useless. Only information counts. Because whenever someone tells you that he is operating on a huge amount of data, like 100 million of rows, thousands of tables, and having these nice informations of numbers, strings, and hex codes, and addresses, and all this is a useless thing. The only thing which counts is the information retrieval. So, and an information is something like this. So customer A has some trouble, especially if he enters radio cell B during business hours because he's using an old-fashioned smartphone with the wrong setup, and additionally his office location has a bad radio coverage. This is an information. So that's the reason why I'm saying data is useless, information counts. So you must retrieve information out of big data, and whatever you do, it only makes sense if you have something like such an interesting information. So this is a business case, and then you can make your customer happy. So now let's talk a little bit, what kind of data do we have and what are possible use cases? So any network operator has two different sorts of data. He knows something about the user and he knows something about the network. Concerning the users, and this is also you, we know the user identity, we know your number, your phone numbers, your device ID, we know what kind of device you are using. We also have some kind of a location, which is an imprecise location because we only know you are in radio cell something. And this is not a very good precision, but we have a precision of maybe some 100 meters. We know where a person is. We also know the service you're using, so what kind of URL you're using, what kind of addresses you are using. We know something about data volumes, and we maybe especially have personal data, so something like revenues, tariffs, addresses, and something. On top of that, we have a huge amount of network data, which is the status of those network elements I was showing before, performance values, configuration data, all these elements needs to be configured. We have alarms giving us special severe indications from those elements. We have so-called CDRs, which is an acronym for call detailed records. That's basically used for setting up a bill for you, so that every bill is charged with some certain amount of money. And we also have a lot of software logs and traces. And all this together is our network data we are operating on. But we have to be very careful. Network data is personal data because it's data about you, about me, and this is strictly limited. So we have a lot of international laws. It's a very complex field under continuous change. It's also pretty different in different countries. So in China, they have a different view on personal data than we have in Europe. There is a huge amount of restrictions on the use beyond network management. And also the usage of this data requires permission from the customers. Nevertheless, operators have the right to use this data because they can use this data for billing, for fault diagnosis, for the improvement of the network, and also for support activities. Because if you are calling your operator saying, I have a bad connection, please help me, they need to do something with your personal data to help you. There's also a nice and very important differentiation between metadata, which means metadata describes what you have been doing, and the user data. User data is really the package, the email you have been sending, the content of this email. This is really strictly limited, and this only allowed to use with your digital orders according local laws. So this is really a tough area we don't touch at all. Okay. Let's talk a little bit what are possible use cases for doing big data analytics with such telecommunication data. First of all, you can address the network, you can address the customer, you can address some external business cases and some maybe, let's say, innovative new things. So network means you're doing a lot of planning, operation, and security. So this is just the normal work of any network operator. You can also address the customer for product management, customer relationship management, and even service issues. External innovative use cases are public interests and commercial interests. And let's look a little bit to the details here. We will not go through all of those, just to give you some ideas. Radio cell performance. You want to know how your radio cells are performing. This is a pretty simple thing, easy and understandable. You would like to know how many dropped calls do you have in such a radio cell. You would like to see what are high-volume websites, high-volume applications, what can I do to support those high-volume applications? And these are the applications like Facebooks and Twitters and such. Another use cases are from security, how to detect botnets. Botnets are wasting transmission capabilities, so you need to detect those. Product management means you would like to have maybe churn probability to find out which customers tend to leave your network, which customers tend to go away from you as a customer. You can try to segment customers in certain classes, so who are business users, who are occasional users, low volume, high volume users and such. Let's go a little bit to the innovative use cases here. Something like disaster detection. You can use this kind of data to detect disasters just by retrieving this information out of a network. If you have maybe a football stadium, 50,000 people in, and maybe 2,000 in this stadium are calling an emergency number, then this is really something you should take care of. You can also try to find for demonstrations how many people are there. You can supervise traffic, you can detect traffic jams, you can do a lot of things with such data. I'll give you some examples on use cases we did in the NDI project. As a research topic, there was one use case we did which is showing subscriber relations. Any bubble here is a single subscriber, and if you have the right visualization, you can show where are hotspots in my customer group. So especially these seems to be some kind of operating centers, so many people are calling this, or there are others. So you really can show public numbers, which are often called. Next use case, this is subscriber mobility. Here in this picture, any line represents a group of people moving from some point to another point. The color here is showing the direction of this movement. I think red is north-south movement, blue is east-west movement, and you can pretty nicely see at a certain moment in time how many people are moving from which place to another place. This picture was made during morning hours between 6 and 9, and you can nicely see a lot of people are moving downtown to main stations and such. There's another use case, just supervising the network. Here we made a use case, it's a real-time supervision of three important services in the network, which is the voice performance, the SMS, and the packet performance. So this gives you a real-time impression how the network really works. Here we also have a map showing where are the hotspots in the network, and you can also do a prediction how this is going to be resolved and how this works over time. And last but not least, the final picture here is showing a very dense radio network, and here we're mapping certain KPIs to those shadings, and especially the red ones, these are the ones which are hot areas where we have really, let's say, a bad operating network. Okay, so these are possible use cases. Mainly all those use cases have the idea, find out what's going on in such a network, what's going on in my data. This is a very complex task. Let's make a comparison to some other things. Let's say you are developing a board like this one, maybe you're a hardware developer. You develop this board and it's coming out of production, and surprisingly it doesn't work. So what do? Maybe, I'm not sure if some of you are hardware developers. Well, you connect something to it like this one. That's a nice device, you connect to it, you can look for every clock, you can look for every bus, for every signal, and finally you can find out what's going wrong here. If we apply this kind of idea to our operating network, we did the same thing. So we invented something like an analytics engine. So the idea is pretty much the same. We would like to have a universal engine which we can connect to our data and which shows all our data with different flavors. It's very important that we can use all kind of data within this platform. So we don't care if this is something from a network data collector, if we have service KPIs or log or trace files, all this is thrown into this large container and should be made visible. It's very important that we show this data in different forms. So this one is a time series. So we show the data changing over time. That's one important aspect. Here we show the data with respect to locations. So in which radio cell this happens. And here we correlate data to each other, even in 3D graphics, saying how does KPI 1 relate to KPI 2, relate to KPI 3. And by doing this, you get a much better insight into this data. And finally, we select, last but not least, selectable algorithms, like we predict those KPIs. If we know we have a history changing this KPI in a certain amount of time, we predict for the next day such a change or such a value for these KPIs. All in all, the whole example has to be highly interactive. So it's very important that you click on something, that you get this data really in minutes or in seconds, that you really can work with it like with a debugger system you're used to. This one is showing a little bit to more details of such views. Here you have selectable KPIs. You really can show different values here. Every time series is showing here. On the left side, we have historical values. The different colors show you classifications. Classifications means we show different situations of different KPIs. The purple ones are certainly the ones not critical, and the orange ones are certainly the critical ones. We have an estimation for the future, which is a trend indicator. On the right side, we have the prediction for the next 2 days of this KPI. So this is a pretty complex chart and gives you really an idea what's going on, like this debugging unit I showed before. The same applies if you look to this with respect to locations. So KPIs and values are really mapped to those estimated cell sizes. You can see where this problem actually happens. We have been even mapping 3D buildings underneath this chart, because even knowing if there is a high building or not is something very important if you want to understand this data. Last but not least, correlation view. Here you have a 3D chart where you can really correlate two different, three different KPIs, and the system is marking, and these are the yellow ones here on the upper right side, is marking you outliers. So it's marking you certain radio cells which behave differently than the others. So all these are very important topics if you want to understand this data. And now in the next step, we would like to do some more detailed analysis on such a data, which we call anomaly and root cause detection. Let's have a look to such a time series. So that's a pretty simple thing. Time series means you have a KPI over time. So this is something like a drop rate, an alarm counter, performance value. And this is just simply changing over time. The problem with this approach is we have plenty of those. We have hundreds of KPIs for our radio cells. We have lots of, our time series are very long. We are keeping data for half a year, maybe even 1 year. We are keeping this data in a resolution of 15 minutes, 1 hour, and 1 day. So even every day we have a huge amount of different data. And last but not least, we are getting really millions of time series. Such a time series, and first of all, the problem is really just the amount of those time series. You have no person who's really able to look at all these time series and find out problems and errors. Well, just more information, putting some more information on someone doesn't always help. So this is even more confusing than helping. So, but what do you do with such a problem? What you really want to know out of those thousands and millions of time series, what KPI is operating in normal state or unnormal state? Where are critical situations? When do they happen? Where are they happening? What is the reason for that? And finally, what will happen tomorrow? Do I have the same problem or will it change? So these are the final answers you must find, and you must have a system which is able to answer those questions. Today, or let's say in the past, our answer to those problems were pretty simple. We invented thresholds. So we took the time series and saying, let's invent 2 thresholds. There's an upper threshold saying whenever the KPI is going above the threshold, we will have an alarm. Or whenever a threshold is going below this threshold, we will have an alarm as well. But last but not least, this is a weak concept because the KPI changes over time. Also, the KPI is highly dependent on the radio cell. If I tell you I have 5 dropped calls in the radio cell, this is maybe just a normal case in busy hours here in Wrocław downtown, whereas having 5 dropped calls during night, if I even have only 5 calls in total, this is a disaster. So such stable thresholds is a very weak concept. It's pretty useless. It's hard to find the boundary between good and bad. Which value should you take? Also here, during night, you don't have any calls, and even setting a threshold of 1 or 2 is just wrong. Finally, all this generates a lot of false positives, and this is not a final help. If you look to such time series, there's a lot of hidden information. Hidden information means, maybe this is possibly a sleeping cell, because at noon, so it's somewhere around noon time, such a small amount of drop rates, that's pretty unusual. This is an indication that this this cell is not operating well. Another case, if you look to this bar, you will see in early hours at 3 o'clock, you might have high values of dropped calls. This is pretty unusual because at such a time, you don't have many calls in the network. So this is an unusual situation. And also, long term, the whole KPI is increasing. So the drop rate is increasing very slowly, but continuously over time. Nevertheless, this here is not a sleeping cell, because at 2 o'clock in the morning, or whenever this will be, 1 o'clock in the morning, you nearly have no drops, and a value of 0 is nothing unusual. So, last but not least, you must have something more intelligent with those time series. Today we solve this problem, what I would call experienced eyes. So we put a person in front of it, and the person knows what's going on here. But, again, we have too much KPIs, we have too much cells, we have not enough experienced eyes in our people groups, and it's pretty error prone. So an intelligence system should tell you where to look at, what are reasonable anomalies, where are dependencies to other KPIs, and what are possible reasons for this behavior. I should have an explanation why this happens. So, finally, we can try to solve this problem by splitting up a time series into some kind of seasonality. So we can try to find a season changing over time. We can add a trend on it. And what's remaining would be some kind of statistical noise. You can also use the seasonality, put it to the future, and try to model the behavior of this KPI for the future. And what we finally get is a system which we split up in seasonality, trend, and statistical noise. We set up lower thresholds on the seasonality, and finally we get a corridor of our expectations. And this is shown here. So now the KPI has been changed. We have model seasonality, and the green part here is the corridor of the expected behavior. Now, this example is much more intelligent, because now we can find out this is a sleeping cell, because this is unnormal, this is not expected, because it's falling outside the corridor of expected behavior. The same applies here, because also this is a model violation. So because in these high errors we do not, I just took the wrong button. In these early morning hours we do not expect so much dropped calls, which is an anomaly. And also, this is a long-term trend violation. This is an unexpected high value according to our expected trends. Also, this here is not marked anymore, because here we have pretty low expectations, and the KPI is also pretty low. So we are within our expectation corridor. Okay, these are examples you can do with a single KPI, but you can also find problems with multiple KPIs. If you see those two different KPIs, and one KPI is showing you the number of registered users, and the other KPI is showing the number of dropped calls, you might not see so much interesting here. It's changing over time, and it looks quite normal. If you look to more detail, there's a problem here, because here the number of dropped calls is pretty high relative to the number of total calls. So we must also find a system retrieving this, and you can retrieve this by doing a clustering across multiple KPIs. I also have been giving you examples where we want to predict KPIs, and this is important. And I would like to give you also some business reasons for this. If a cell is not working properly, this is really a disaster, because the impact is on a large amount of customers. Even if you rapidly realize such a problem, it's always too late, because it already happened. And last but not least, if you have lost a customer, you have very high acquisition cost for new customers. In Germany, if you're getting new customers, you have to offer him new handies, new mobile phones and such, which is very expensive. So you have to prevent losing customers. That's very important. So the idea to change from a from a mode where you react on problems to a mode where you preventively try to detect or forecast problems is very important. So finally, we would like to make an estimation which cells are in trouble tomorrow. Finding out which cells have been in trouble yesterday, that's a nice task, but it's more or less useless, so we have to find trouble we will have tomorrow. Then we have a chance to react and change it maybe accordingly. Now, machine learning comes into play. As I said, we have been modeling these KPIs with seasonality, with long-term trend. We have been putting lower and upper thresholds on it. And finally, we have been modeling this model of this corridor of expected behavior. The algorithms used for this are written here on the right side. So trending is a simple thing. It's a simple linear regression. The seasonality can be modeled with one of those 4 different algorithms of k nearest neighbor, decision trees, non or linear regressions, or logistic regressions. There's one problem remaining, that you have to have this kind of model hundreds of times, or thousands of times, because you have 50,000 radio cells. Every radio cells behave differently, has a different model for the corridor of expectations and such, and you need to retrieve all this into something which is more intelligent. To give you an idea how this looks in reality, this is also a picture from our research project. Finally, we have been doing exactly the same thing what I reported before. So here we have those KPIs. This is a KPI showing how much failures have been happening in the handover between radio cells. The system has found here we have been leaving this corridor of expectations, which is the gray area in the background. So here we have 2 cases where we have been left this corridor. We also have a case which is marked orange here, where we have a combination of those 2 KPIs, which are unusual. And all these retrievals are finally marked in a set of messages where we show where are model deviations, where are alarms. And finally, we have an intelligent system which takes all these data, all these KPIs and time series, and really retrieves more or less such intelligent messages, really pointing to those problems where you have to look at. Okay, now let's go to the next step. Now we have been detecting problems. Next interesting thing would be, how can we explain those problems? How can we explain what was going on and what to do with it? So we need to locate the problem. We need to find out what are involved systems for this behavior. We need to make references to specific customers, to specific device types and such, and then we really can derive an important action out of it. So having a KPI is not sufficient. So if you know that the drop call rate in cell A is too high, that's good to know, but the problem is, what should you do? How can you solve this problem? So reasoning is important. Why does it happen? What is driving this problem? Is it periodic or a one-time problem? And what do I need to do, and how can I change it? Let's have a look to just a simple table. You're getting this out of one of our systems. So here we have so-called handover failures marked. 1 shows you this is a handover failure, 0 shows it's not a handover failure. And you have some certain features and more information. You know the reason explanation, you know which kind of device is involved, at which time it happened and such. Huge information. And the table is about 5,000 messages long. If you look at it, you won't see anything. You can solve this graphically by making, or let's say deriving, certain dimensions out of it. And here you will see that, first of all, this problem is increasing over time. So you have more of those problems in late hours. You also have a peak weekday, which seems to be a Thursday. If you look for the dimensions in which cell it happened, you clearly can see there are certain cells where there's a higher involvement. So you have some cells where this happened much more often, like this one, also this one, and the others one are more or less normal. And also look which derive, by the way, BSC is a base station controller, so this is a controlling unit in our network. So you will also find that the number of BSCs is not unequally distributed. So you have 3 BSCs which are causing this problem. So you can solve this with a lot of graphics, but you can also solve it with algorithms. Let's take this table and throw it into an algorithm. And the algorithm will tell you that you have a strong time dependency, which means this really happens at a specific time. It will also tell you there is a high tendency for those 3 BSCs that this problem happens. And then you can go down this list and you will find all factors driving this problem. So that's what we call a root cause analysis. Last but not least, have a short look from machine learning perspective. What are the algorithms we have been using? So for doing this kind of model deviation, we are using nearest neighbor algorithms. For the trend violations, we are using linear regressions, classification errors, dbScan, root cause analysis, Gaussian naive Bayes. It's tough to explain all these algorithms here. It's very important that you have a machine learning background in doing this. This is more how you can apply it. So let's summarize a little bit what we have seen so far. So we have invented a system which is taking single KPIs out of an operating network. We have been training a model for the expected KPI behavior. We have been doing an anomaly detection. We categorized the problem in an OLAP cube. And finally, we have really found out where are our problems. And for last but not least, we have been able to reasoning what's going on in that system. Well, in the next step, I would like to show you a little bit on time series analysis. As I said, time series are very important for us, and even the prediction is very important for us. So how do you predict a time series, a value changing over time? A time series is a simple thing. So you have a time, and you have a KPI over time. Prediction can be done with a method called ARMA, auto-regression moving average. And the idea here is that you first add moving averages to this kind of time series. So on top of the KPI value, you're adding a moving average window, smoothing a little bit the change over time of this KPI. After you have done this, adding the moving averages, then you will add a so-called lag window on it. Lag window means you're finally mapping those values from the lag windows. Here you map it horizontally into this feature vector. And these are the lag window of the normal KPI values, and that's the lag window of the average, or the running average window. Then you throw this into an algorithm. And this could be something like neural networks, nonlinear regressions, logistic regressions, decision trees. And last but not least, you are able to make a prediction on such a time series. I can show you a little bit picture here. Here I was drawing the time series of different cells. So every color stands for a different cell. So the KPI is changing over time. Whenever this is marked with an explanation mark, it is predicted as being as a violation. So violation means it's crossing a certain boundary, and it's marked as a bad behavior of the network. And you nicely can see that we really correctly are able to predict such situations. By the way, this is a 1 hour prediction. And that we also have no false positives, because here we only have one system which is just for 1 hour, an outlier, but this has not been predicted. So pretty nice and complex work, but finally you are able to generate lists maybe for the next hour which radio cell is going to have problems. Now let's talk a little bit how we do this. I think a lot of you are software developers or have software development background. It would be useful to have a look on this. So these are use cases, what we do. And now let's talk a little bit how we do it. Well, you certainly need use cases, and I think we spend a lot of time now on those use cases, what you can do with machine learning in telecommunication space. To make this happen, you must have certain technology enablers. First of all, you must have the methods like data mining, machine learning, statistical, predictive analysis, and the appropriate tools for that. You must be very good in storage, processing, and representation. I think also the examples showed taking all this data, putting it into storages which are easily accessible, very fast, show different flavors and views of the same data is a very demanding task. Also having all this processing done, and here you have to talk about Hadoop engines, real-time analytics systems, which work in combination with data warehouses, NoSQL databases, Hadoop stores, column stores, in-memory databases, and such. And if you have processed all this data and stored it, you must have good ways of finding the correct representation. I hope also you have seen those examples. A correct representation, a fancy representation showing you time, showing you the aspect of locations, showing you changes, correlations, and such is very important. So visualization is a big, big topic here. So what do you need to do to have such a big data analytics stack? In telecommunication industry, we like a lot stacks, so systems which have different layers responsible for a certain functionality. And before you can start, you need data sources. You need all this data out of the networks, which looks as a trivial task, but in reality, this is really a tough task. So retrieving all this data out of a telecommunication network is really demanding. So until you have it on your desk. And if you have really fetched it, you need to do some kind of import, you need to have a formatting on it, type conversions, which is an ugly and demanding task. By doing this, you need a lot of aggregation, filtering, distributed computing to make this happen, because we have tons of data, gigabytes and terabytes of data, and this must be very efficient. Because if you have a nice machine telling you there was a great problem 3 weeks ago in your network, this is useless. So it only makes sense if you are able, from an event which happens in the network until you see it on your screen, if you have maybe 2 minutes. And then everything has to be done. On top of this aggregation and filtering, you have data storages. You must use a relational or NoSQL databases. And then finally, you can apply such fancy algorithms like k-means, decision trees, and such. And last but not least, you must have a good visualization on top of it, that you can make it visible, that you really can show what's going on in this network. And on top of that, you have certainly a use case. Now, from a developer perspective, let's have some words. What is a development effort? So how does this relate to development efforts? Interesting to see that the application of such intelligent algorithms, that's a pretty simple thing. There are nice libraries. You need to understand those algorithms, which takes a lot of time and experience. But finally, the application is pretty simple. But all the other tasks, preparing data, processing this data, bringing it into the right form, and on top of it also have the right visualization for this. This is really demanding and takes the most efforts. Now, let's have a look what are possible software pieces which can cover this big data analytics stack. There's a big tool, a big group of analytic tools. I think the Philip didn't mention those in his talk before lunch. There are tools like RapidMiner, NIME, SPSS, which are really made for doing analytic jobs. Later on, I'll show you one picture for that. Then you have some kind of mixture made out of some kind of processing out of Hadoop and Storm, Pig, which is doing importing and formatting, Hive, which is an SQL type layer on top of Hadoop, Mahout, This can apply machine learning algorithms on a Hadoop environment. And last but not least, you can use tools like Tableau, ClickView to make this visible in some visualization form. The problem here is that those packages only cover certain parts of this stack and not everything. Beside this, there are the so-called language stacks, and we also heard already something about R and Python. So R is very popular. This is a very specific stack for doing data analytics, but also Python is coming into play pretty much, especially together, and this you already have heard with Philippe's talk, which is together with Pandas and Scikit. Beside this, also a lot of databases are claiming they are big data databases and ready to use for big data processing. And these are the ones from Teradata, Oracle, but especially NoSQLs and something like Vertica. Well, some comments on these different tools again, especially the knowledge about analytics algorithms. This is really something you need a very good analyst background. So this is nothing you can learn in a week. Here you must really know and learn algorithms. You must understand those algorithms. And if you look to those algorithms, they really start with a lot of mathematic formulas. So these are really hard to read, but you have to go through to get really an understanding of this. Those tools, they are pretty nice. They can do and apply a lot of algorithms on data, but they all have problems with big data. So they are really not made to work on tons of data. They are more for taking an Excel sheet, throw it into an algorithm and get something out. So they are not optimal. Hadoop is very popular, but it's only parallel processing. So Hadoop doesn't give you so much what you would expect. It only gives you this kind of processing thing, so simple processing. The Mahout is not very popular. It has some machine learning in, but it's not very often used. Well, the language stacks on the right, so R and Python, they have a high entry barrier. You need to understand R. You must be in Python expert. You must be an expert in Scikit and Pandas to get this done. That's not easy. That takes time. And last but not least, all these databases, that's a pretty crowded space. They claim they can do everything, but finally it's a pretty, as I said, crowded space. Pretty confusing. Well, here I would like to give you some overview. Yeah, okay. Would like to give you an overview on such a data mining tool. This tool is called KNIME. That's an open source tool. It's pretty simple to be used because it contains building blocks, small building blocks, which could be simple conversions from numbers to strings, so data preparations, aggregations of data, join and pivot functions, retrieving something out of a database, and last but not least, you really can apply machine learning algorithms. So here you are applying a nonlinear regression on this data, a linear regression or a decision tree on this data, and you get something simply out. So nice tool. Cannot deal with big data, but if you complement this with a powerful database, this really works very nicely. Concerning graphics, this is a picture from Tableau. This gives you an idea why you need such a tool. Here again, every color stands for different radio cells. The radio cells are listed here on the right one, so every color here is a different radio cell. Why do you need such pictures? Because you need complex pictures to get something out of this data. First of all, you will see we have missing data here. So we have some time slots where we're missing data. You can also see, even in those crowded pictures, that you have outliers. Yes, you can see those orange cells. They seem to behave from the first view. They seem to behave differently. So these are pretty different. You can also see you have certain times where the total number of KPIs are much higher than before. This is a KPI peak here. You can also see that you have nearly no seasonality in this data, so it's pretty constant and stable over time. Having a tool showing you such very complex situations of data are very important. This tool is called Tableau. There are also others as well. This is called ClickView. This picture was made to find out if alarms correlate with KPIs. So we have from our radio cells, we have KPIs. We have KPIs telling you we have a drop rate, we have a number of registered users, and we are also getting alarms showing you there is really something important happening in this cell. This picture on top is showing you, here we have 4 KPIs, and high values means we have trouble, we have problems with this KPI. And behind it, we have the alarms. What you suddenly see with such a picture, that we have a very weak alarm status, which means here we have cells which are in trouble where we have alarms, but here we have a lot of cells which are in trouble where we do not have alarms. This is really tough to find out if you have not such graphical tools. So graphical tools are very important to understand data. And if you haven't understood the data by yourself, you cannot expect that any algorithm will understand it. Okay, let's talk a little bit about final choices, how we do our analytics. So as the picture showed, we have been using a lot of RapidMiners and KNIME as analytic tools, whereas we see those tools as development tools. So we take those tools to get an understanding of data. We also take Tableau and ClickView to make graphics for this data, to understand it, to really see where are problems, where is data missing, where does it fit together, where doesn't it fit together. Finally, we do everything with Python because we found this the best solution to apply machine learning algorithms in a very smart way. And last but not least, we are using some NoSQL databases and also SQL databases for our data storage. For this NDI project, we invented a software architecture which basically contains different parts. So we have a so-called distributed real-time importing unit, which takes all this data, does input formatting, aggregation, and filtering. Then we have a server system, which does all the data storage into NoSQL or SQL databases, and also applies analytic algorithms. And on top of that, we have a rich client approach where we do all these kind of visualizations. And last but not least, on top, we have done certain use cases. Some of those use cases you have seen in the pictures. In reality, this software architecture looks like this. Again, we have those 3 parts. We have a real-time streaming, which is written in Python using pandas and scikit. We have a database server, also using Python, scikit, and pandas. Django, for those people who are not so heavily involved in Python, this is something like Tomcat in Python. So this is a web server environment for Python. Last but not least, we have different databases underneath, which are MySQL or MongoDB. And all the graphics is done in a rich client approach. So we do all kind of graphics in browsers, in locally rendering browsers. Good. Last but not least, here we have a development environment where we use those graphic tools, understanding data and making trials with the data we have. Well, now let's talk a little bit about those components. First of all, about Python. So why did we use Python? First of all, we wanted to have something for rapid prototyping. That's very important. So by the way, all these examples have been done with 3 or 4 people. So this was a very small group doing all this kind of development. And they have been generalists, so they have to be working with databases, with machine learning algorithms, graphic tools, Python programming, and all these. But last but not least, we have been a very, very small group. So Python has a very high functionality. It's pretty much suited for data analytics. It contains statistical computing, text mining. It's something like a modern R. So R is a little bit aged from the structure. I think Python is much more intelligent. It also contains a lot of next generation programming aspects, like is object and functionally, it's object oriented, also supports functional programming. It contains closures, duck typing, automatic memory management, lambda functions. So all those nice things a lot of people are looking for are already included in Python. It also has a huge library and community. It uses most clips on Linux, and therefore it's very fast. And it also has a lot of communication stacks, encryption function. So whatever you need, I think it's available in Python environment. And on top of that, it also supports server programming. So we have this kind of Django approach, or Twisted, which is event-based, whereas Django is plain HTTP-based. And so for that reason, it suits pretty well for development. I also like this picture. This is from a German master thesis, and in this master thesis they have been written different single programs and in different languages, and this picture shows a little bit how many code you need to implement a function. And here you can see that, for instance, in Java, the spread, how many lines of code you need, is pretty going wide. In general, it's much higher than for Python or Perl. Also C or C++, but in general, you need more code to do something in Java, whereas Python is pretty dense, so it's really very small. A lot of our server programming was really done in 20 lines of code, very, very small amount of code. And last but not least, I have always this in mind from Google, where they say we use Python where we can and C++ where we must. So I think this is a very important statement. So if you have to have some certain constraints, then use C or C++. But if you have the freedom to go a little bit further, then use Python. Okay, what are possible counter arguments against Python? First of all, speed. A lot of people would say, well, this is interpreted. If you have big data, this doesn't make sense. For that reason, I would say think big and optimize your algorithms. So think how you do things. We have been able to solve every problem concerning speed, and also use the full potential of your database. So if you have a tough database, you should also put a lot of load onto this database and not do it on your own. Also, parallel programming seems, or let's say it was often seen as a problem for Python. Here, I'll later on show you one example how we did it. So you can use secure message passing. So you don't have to use threading in your Python environment. So you can also come around this. The Python 2, Python 3 incompatibility was a tough problem, but I would say this is today more or less done, and most packages today have Python 3 support. Last argument, Python is unstable. That's nothing for product development. I think this is just wrong, because what we did so far, and that's our experience, what we did was working from the very beginning. We had no problems with garbage collectors, strange bugs or problems or whatever, so it just worked from the very beginning, so we liked it a lot. And last but not least, our programmers love it. So we have been changing some people from Java environments, and after 2 or 3 weeks they say, well, this looks nice. I wonder why I haven't used this before. So, some words about Pandas and Scikit. So why are those two packages so important to do this kind of machine learning? First of all, Pandas is some kind of R extension for Python. So it's last but not least something like an in-memory SQL. It's very fast. It internally uses native C arrays. It's introducing complex data structures like time series, 2-dimensional data frames, 3-dimensional panels or 4-dimensional arrays into Python, which you can use pretty nicely for those machine learning tasks. It supports vector operations. You simply can multiply column A with column 2 with a single statement. You can do computations across rows like moving averages and such. Pretty simple. It has a lot of descriptive statistics. It can support group by, sort, and indexing. So whatever you do with a database can be done with Pandas. The interesting thing is with Pandas, it does it in memory, so it's extremely fast. So you can take 1 million number of rows in memory and just aggregate this in a second or so. Let's go to Scikit. So Scikit contains all those nice algorithms I have been showing. Something like decision trees, classification, nearest neighbors, random forest, regressions, data preprocessing, neural networks. It is not written here, but it contains nearly everything what's available. The problem here is not more to use it, the problem here is to understand it. So a scikit application could be 10 lines of code, but I guess you would take 2 weeks to understand it, because you must have a very good background what's really going on in this algorithm. So let's talk a little bit about our importing function. Finally, what the importer function does, it takes data from the network, so our voice and SMS data from our gateway systems, from HTTP and DPI, so deep packet inspection system, so what we get. And finally, the importer is setting up an OLAP, an n-dimensional cube, doing aggregation on certain levels. And those levels could be, first of all, could be an aggregation maybe on CGI, URL, EMI, which would be, we can aggregate on a customer level, we can aggregate on a radio cell. On the second dimension, we always aggregate on time, because we are collecting those events for 15 minutes, for 1 hour or 1 day. And finally, we're getting this n-dimensional OLAP cube, which is done with our import function. The import function internally looks like this. So finally, it does a data read. So it takes data from any kind of different sources, what we have. So we're reading from databases, from URLs, from sockets, from files, or whatever what we get. We have 2 main phases. So first of all, we use a lot of pandas code for type conversions, filtering, aggregations, joins, pivotings, and last but not least, we apply scikit code and doing supervised learning, unsupervised learning. We apply models and do data transformation. And last but not least, we write it to some database. Processing is a big problem because we have a huge amount of data. We have a huge amount of sources. We might have, 20 different sources. And those sources are really from that nature that they are sending you events per second. Such a source might give you 10,000 events in a second, and you have to process those events. For applying this, we have a system, this real-time importer has so-called engine feeders and engine workers. So the engine feeders take the data, finally just read it, don't do so much with it, and put it into a message broker. The message broker distributes it on different systems, where we have a whole bunch of workers operating all those different sources, doing aggregations, filterings, type conversions, and whatever. And finally, the result is written into our server system, and then you can see it. This also shows that this is really a scaling system. Finally, we achieved about 150,000 messages in a second on a 4-server system, which is pretty nice. And it's also scalable, you can extend it. This kind of parallelization in Python is done with 2 systems, which are called Celery and RabbitMQ. Celery is also a part of Python. It's a distributed task messaging. It's pretty tightly integrated into Python. You define a function in Python, and you just add an annotation on top saying this is a remote task. And then you can use it in another task just remotely and call this function as a remote procedure call. It's pretty nicely integrated, very powerful, and it also supports different kinds of several message brokers. So we have been using RabbitMQ, but it also supports Redis and others. And it's working within a node, so intra-node, and also between nodes. You can really distribute those functions on 500 nodes, if you like, and you have a central message parsing function. Well, RabbitMQ is our message broker. This one supports different communication patterns, so it's a 1-to-1, 1-to-n, n-to-1, publish and subscribe pattern. It supports multiple queues, has a very complex message routing. You can even apply priorities on it. It works on a standard like AQMP. And it's also supporting multiple language, so a sender can be written in Java, whereas a receiver can be written in Python and other combinations. And internally, it's written in Erlang, which is a little bit interesting thing. So now let's talk finally a little bit about our rich client development. You have been seeing that we spend a lot of time in showing the right graphics, making this interactive. And we spend a lot of time how we do this. So we don't have really a client providing this functionality, so we do this as a web function, as a web application. Some basic thoughts about a browser. So you might see this as an application tool to browse on websites, but this is also a nice application environment. So it's really a virtual machine. It's a container for complex applications. It's also standardized. It supports 3 different domain-specific languages, which are HTML5, CSS, and JavaScript, where HTML5 describes the structure of your application. CSS shows you the look and feel, how this looks like in reality, the colors and the boundaries and such. And JavaScript just defines the behavior of the application. And on top of that, it comes with a very complex and powerful development environment. It's extremely fast and well tested. It's available everywhere. So a browser is available on PCs, on tabs, on mobiles. So if you have written such a functionality, this works on the top as well. I didn't have a picture with me, but that's what I showed before. Those nice pictures, they have been showing on Samsung tablets. No problem, this works. It's also nice for our customers to show we are doing big data on small tablets. So. Good. And last but not least, all this is for free. So our browsers are really one of the most important and let's say powerful development environment you can think of. Here is also the structure written of this browser client. Here you can see this is all based on JavaScript, HTML, and CSS. We are using certain libraries like OpenLayers, HighCharts, D3, Angular, and OceanTouch. So this is much more complex than what we do in our server. And the idea is here really to have something highly interactive and powerful with respect to graphics. Before you start in web application development, you need to think about, do you do client rendering or server rendering? So do you do everything on the server and you just deliver ready-to-use HTML on your client? Or do you do a lot of client rendering, which means everything is running in the browser, so everything is rendered in the browser? If you do server rendering, you do the whole rendering on the server and the full web page is downloaded. This would require something like Java server pages or portlets. The advantage is you have only server programming. You only have to write some Java code or whatever you're using. The big disadvantage is every interaction has to run across the server. If you click on something, you have to do the request on the server, do the rendering on the server, and load it down. You also do not have local interaction, so it's really hard to make something, let's pop this up, let's change the view and make this very fast. So then you always have this kind of very slow working style. You need to click on something and it takes, 10 seconds until you see something. Mostly data is embedded in the DOM environment. And first of all, it's less interactive. For that reason, we didn't like this so much. We have been deciding for client rendering, so which means we have to write a big JavaScript application, which is loaded via HTTP. You have to have something like a client framework, which is in our case Angular or Ember. Last but not least, you're getting a very complex JavaScript application. So every trigger can be handled locally. It's extremely fast. You click on something and it just changes. You're getting the data access via JSON function and asynchronous HTML requests, which is extremely fast. It's also hidden. The user will not see it. The disadvantage of it, you will get lots of JavaScript, which is a tough thing to handle. But finally, this really behaves like an application. Good. Some words about JavaScript programming. First of all, this is not a toy language. This is really a reasonable language for application development. I guess right now it's number 8 in TOBE index, which means it's really used for heavy development. It's standardized. It also supports functional and object-oriented programming, has modern features like closures and such. Dynamic typing, and it's interpreted and broadly available. And there is a huge amount of upcoming frameworks to support this for charting and Angular and writing applications in it. So all in all, you can say JavaScript is really hot. You might be surprised about this, but it's really a tremendously improving environment and heavily used by lots of different applications. Some words about how we did all this kind of graphics in our client. So we have been using 3 different libraries. So there was, first of all, OpenLayers, which you can do all kind of maps and also graphics on top of maps. You can have certain shadings, and we did the estimation of the cell sizes here. You can have different maps, Google Maps and OpenStreetMaps and whatever you like. Then we have been using HighCharts. HighCharts is a very complex library for doing all kind of charts here. Maybe you remember this example. This is also highly interactive. You can, for whatever, so whatever you click here, you will get some change. So you can really zoom into some time series. You can switch some things off. Whenever you go with the mouse on top, some window pops up, shows you the values and such. That's a very powerful thing. Pretty complex, but it can do any kind of charts you would like. And last but not least is D3. So whatever cannot be done with HighCharts, D3 can do it. So D3 is a very popular graphics library where you can do some very specific things like this kind of view, which is a so-called force-directed graph, or very strange trees, and this is done with the D3 library. Good. Last but not least, the complexity is increasing. So maybe OpenLayers is a pretty simple thing, but D3 is pretty heavy to use. Well, my last slide, my previous last slide. Some words about Angular. I'm not sure if you know Angular. Angular is a model view controller framework used in browser environments. It's very important to have this. Last but not least, it's something like Tomcat or JBoss for rich client development. So also today, nobody would do some kind of HTTP development from scratch. So you use Tomcat, plug in your things, and the same thing applies to Angular. Angular gives your application a nice structure, which is very important to keep this clean and also maintainable. It's a great simplification for the development, and it also reduces the amount of necessary JavaScript code to a large extent. Finally, it's a model view controller architecture. It has a two-way binding. It gives you the combination between, let's say, the relation between your JavaScript variables and the DOM, the HTML entries. You can do very nice things, and you can also use this especially to reduce the amount of code you need to write. So there's no way around Angular if you want to be successful here. Well, I'm coming to an end here. This is my short wrap-up. We have been looking a little bit to telecom space, how this looks like, what kind of data we have, so what data we are working on, also what are our use cases, what do we want to do with machine learning in this environment. We have been talking about analytics, and last but not least, what's the software and what are the software pieces you need to do to make this working. And last but not least, thanks for attending. Do we have some minutes for questions?
Yes, absolutely. We have 15 minutes for questions, so a lot of time. If you have some questions, just raise your hands and we'll pass on the microphone. I can't see any. Seems like that was a very good insight with a lot of information.
There's one here over there.
There's a question.
Hello. You said that this is still running a research project.
Yeah.
So what about the product? What's the money that it will bring, or you support, let's say, one customer? What about a few hundred that you have? as your client?
We are in discussion on making this a product. We have already some products doing analytics. We are still fighting what's the right way to do it. Also inside Nokia, we have a lot of discussions if we have to use R or an external tool or Python. This is still a lot of discussion. We also have a large party of people saying, well, everything has to be done on Hadoop for whatever reason. So that's still tough. So, but I think the idea of this research project is really to show how to do things, to show possibilities, what you can be doing. Especially this, what I showed with this kind of modeling, expectations, prediction, that is pretty new and innovative. And we got the feedback from our people saying, hey, this looks great. This is something what we need. So, because what we have so far as products is much more dumb than you would expect. So this is not that fancy. So there's a lot of demand for having more intelligent functions.
There's another question.
Hello, I would like to ask about the single events, how the single events affects the data. Also, if these events are completely ignored or, for example, processed in a different database.
I'm not sure if I got the question, so...
I mean, we have a single events in a communication. For example, we have a conference today, and we have a large crowd in this area. So this is not usually the case. So these events are...
okay. Yeah. I know what you're meaning. Well, you certainly need to have calendars, and something like event calendars in this kind of seasonality. You maybe remember this seasonality. So we extract this seasonality component from the last week. So we are learning from the last week, and we are taking this as a seasonality. Which means if there is maybe every Saturday afternoon a football soccer game in a stadium, then you will get this as an event. If this is a one-time event in a year, maybe New Year or something like this, you don't get it. There is the idea of adding event calendars to the system that you learn from the past, but you also take triggers which are occasion events into the system and add it to the modeling. So this kind of modeling, there are a huge amount of ways to improve it. What I showed is just maybe the very beginning, learning from the last week or the last 4 weeks, getting a season component and also a trend component, retrieving it and taking this for forecasting. Having a season calendar, like maybe the season calendar would include all the soccer games, would include all kind of holidays, national holidays in the country. This would become much better.
Also, I would like to ask if the data from those events are processed in a single database later, or, for example, if they're how to change the structure of the stations if there is some kind of emergency. So if our network is ready for this kind of events, so those data are processed later or completely ignored?
Well, currently we do not support this kind of idea. It's definitely, I think it's a good idea. No doubt about this. Currently we don't have it. I think we would need also some kind of incremental add-on of such calendars in the data. After you processed it once, to have between, let's say today we have season component, trend component, and noise. And noise is just useless because you cannot say so much. Maybe we would need to add a fourth component saying these are occasional events. some kind of function where you have peaks and you're overloading those peaks on top of it. So this could be a solution.
Thank you very much.
But there's plenty of room. And by the way, whenever we show this to customers, people start to invent something and say, hey, if you would take this data, could you do something like this? And so, because whenever people see this, they have ideas how you can improve it. So it's definitely something which drives also innovation just by showing it. So what you could do with it. Okay?
Okay, do we have any more questions? Final call for questions? Okay, so that was Norbert Kraft with Big Data Analytics in Telecommunication.
Okay, thank you.